Hello everyone, I'm Dr. Manhal ABOUZLAM. Let's answer this question. What's the principle on which the function Bode in Matlab is based? Suppose for a transfer function you have this contour map in complex plane, where the frequency varies from 0 to infinity in this direction. Let's focus on the phase in the frequency response, because with the phase we often find problems. In fact, when you apply the function Bode in Matlab, you obtain this curve for the phase. As you see here in the contour map, when the frequency varies from 0 to infinity, the contour moves in a negative direction and it does a complete turn. And that's what we see here in this curve. From the frequency 0 to infinity, we start with the phase 0, then we arrive at negative 90, then negative 180 until negative 360. So as you see here, this curve really represents the movement of the contour, and it is a continuous curve. There is no problem. Now when you try to program in another programming language like C or C++, when you try to apply what you learn in university, you often obtain a curve like that for the phase. It starts with the value 0, then arrives at negative 90, then from this point and suddenly it jumps into 270. Then it goes down until 0 when it does a complete turn. In fact, as you see, this curve can represent the movement of the contour, but it's not a continuous curve like the curve which is given by the function Bode in Matlab. And this curve can make the calculation of stability margins difficult. So the question is, how is the function Bode in Matlab programmed? What is its principle? How can I program, for example, in C or C++ in order to obtain the same curve that the function Bode in Matlab gives? Firstly, I show you what they often teach you in university, and therefore why with what you learn you can't obtain the right frequency response, the frequency response that the function Bode in Matlab gives. Let's take this developed form of a transfer function. In fact, they ask you to replace the Laplace variable s with gw. Then they ask you to write this transfer function like that, where you have a real part and an imaginary part. Imagine here this transfer function has this contour map. So for a given frequency you have here this real part and you have here this imaginary part. As you see here, this length corresponds to the magnitude which is given by this equation, and the magnitude in decibels is equal to 20 decimal logarithm of this length. Now with this equation you can plot the magnitude in decibels as a function of frequency. In fact, there is no problem with this method. You can obtain the same curve that the function Bode in Matlab gives. Now for the phase, what do they often teach you in university? In fact, for your transfer function that you have written like that in this form, they ask you to apply the following strategy. If the real part is positive, so the phase is equal to the inverse tangent of this ratio. But if the real part is strictly negative, so the phase is equal to the inverse tangent of this ratio plus 180. Just a little note, for the programming languages, the inverse tangent of a number is between 0 and 90 if this number is positive. But if this number is negative, so the inverse tangent of this number is between 0 and negative 90. Now let's discuss the strategy. Imagine here we have this contour map for our transfer function. In fact, when the real part is positive, we have two cases. We have the case where the point on the contour is in this region, in this quadrant. And we have the case where the point on the contour is in this region, in this quadrant. Now for the case where you are in this region, the phase is equal to this angle, because as you see here, this angle is equal to the inverse tangent of this ratio, imaginary part over real part. And as this ratio is positive, so this angle, this phase varies from 0 to 90. Now for the second case, where you are in this region, the phase is equal to this angle, because this angle is equal to the inverse tangent of this ratio. And as this ratio is negative, so this angle is negative. So the point in this region varies from 0 to negative 90. Now when the real part is negative, we also have two cases. Either you are in this region or in this region. For the case when you are in this region, the inverse tangent of this ratio is equal to this angle. As this ratio is negative, so this angle is negative. When we add this angle to 180, we obtain the phase which is equal to this angle this inverse tangent, which is between 0 and negative 90 plus 180, so the phase in this region is between 90 and 180. Now for the case where you are in this region, the inverse tangent of this ratio is equal to this angle. As this ratio is positive, so this angle is positive, and when we add this angle to 180, we obtain our phase, which is equal to this angle. This inverse tangent, which is between 0 and 90 plus 180, so the phase in this region is between 180 and 270. In short, when you apply this strategy to the real part and the imaginary part of the transfer function, so the phase in this region is between 0 and 90, and in this region is between 0 and negative 90, and in this region is between 270 and 180, and in this region the phase is between 180 and 90. That's why when you apply that to our example, which has this contour map, you obtain a curve like that. You start with 0, then you arrive at negative 90, then suddenly you jump into 270, then you arrive at 180 until 0. Okay, this is the curve that I showed you from the start. But when you apply the function Bode, you obtain a continuous curve like that. You start with 0, then you arrive at negative 90, then you arrive at negative 180 until negative 360. Now I have shown what they often teach you in university, and that's why you obtain for the phase a curve which is different from the curve that the function Bode gives. So the question is, what is the principle of the function Bode? How to program in order to obtain the same curve that the function Bode gives? In fact, the principle is to apply this rule, but not for the real part and the imaginary part of the transfer function, but for the real part and imaginary part of each polynomial of the factored transfer function, where all the factors have to be polynomials of degree 1. What does it mean that? Let's explain in detail and present the strategy. Firstly, we write the transfer function as a factored form where all the factors are polynomials of degree 1. Each polynomial is written like that, s plus a number. This number can be a real number, can be a complex number. Then we replace the variable s with gw. Then we write each polynomial as a real part as a function of frequency plus g times imaginary part as a function of frequency. Now for the phase we apply our rule that we have already explained, but now for each polynomial. We apply our rule for each polynomial and we find the corresponding phase. Okay, we apply our rule for the real part and the imaginary part of each polynomial, then we find the corresponding phase. Just a little note for this gain: if we have a positive gain, so the corresponding phase is equal to 0, but if we have a negative gain, so the corresponding phase is equal to 180. Okay, now we add all the phases for the numerator and we find the corresponding phase, and we add all the phases for the denominator and we find the corresponding phase. Finally, the phase of the transfer function is equal to the corresponding phase of the numerator minus the corresponding phase of the denominator. Now for the magnitude in decibels, you can apply the method I already explained for the developed form of the transfer function. But if you have a factored form like that, you calculate the magnitude in decibels for each polynomial of degree 1 and you find the corresponding curve. Then you add all the curves for the numerator and you add all the curves corresponding to the denominator. So the magnitude in decibels for the transfer function is equal to the curve corresponding to the numerator minus the curve corresponding to the denominator. Now let's take some examples where we will focus on the phase because you often find difficulty with it. And in these examples, we will try to discuss all the difficult points you may encounter. Let's take this transfer function which is given as a factored form. In fact, just in order to save time, I directly gave the factored form. So verify that all the factors are polynomials of degree 1, where each polynomial is plus a number. This number can be a real number or a complex number. Now we start with the numerator. We have a gain which is positive, so the corresponding phase is equal to 0. Okay, now for this polynomial s plus 1, we replace the Laplace variable s with gw, so we obtain the real number and the imaginary number. Now for the frequency from 0 to infinity, we program our rule in order to find the corresponding phase. If you want, I can show you how to plot it by hand. Look at that. For the frequency from 0 to infinity, the real number is always positive, so the phase is equal to the inverse tangent of w. So for the frequency from 0 to infinity, the phase varies from 0 to 90, okay? Now we do the same for the polynomial s minus 2, and we obtain its real part and imaginary part. Then for the frequency from 0 to infinity, we program our real and we obtain the corresponding phase. Now how to plot it by hand? Look at that. For the frequency from 0 to infinity, the real part is always negative, so the phase is equal to the inverse tangent of w over minus 2 plus 180. So for the frequency from 0 to infinity, the phase varies from 180 to 90. Now we start with the denominator. Let's take this polynomial s plus a complex number. We replace the variable s with gw, then we obtain the real part and the imaginary part. Then for the frequency from 0 to infinity, we program our real in order to obtain the corresponding phase. Now how to plot it by hand? Look at that. For the frequency from 0 to infinity, the real part is always negative, so the phase is equal to the inverse tangent of w plus 1 over minus 2 plus 180. So for the frequency from 0 to infinity, the phase varies from about 153.4 to 90, okay? Before continuing, just a little note. Pay attention, if your programming language gives you the inverse tangent in radians, so you have to convert it into degrees. Quite simply, you multiply the inverse tangent by 180 over pi. We continue with our example. It remains for us this polynomial. We did as before. We obtain its real number and imaginary number. Then for the frequency from 0 to infinity, we program our real. Then we find the corresponding phase. How to plot it by hand? If you observe, the real number is always negative, so the phase is equal to the inverse tangent of w minus 1 over minus 2 plus 180. So for the frequency from 0 to infinity, the phase varies from about 206.6 to 90. Now we add all the curves corresponding to the numerator, then we obtain the phase of the numerator. Then we add all the curves corresponding to the denominator, then we obtain the phase of the denominator. So the phase of the transfer function is equal to the curve of the numerator minus the curve of the denominator. As you see here, we obtain the same curve that the function Bode gives, where the phase varies from negative 180 to 0. Before continuing, just an important note that no matter how we choose the limits, the plot must always start at a low frequency, at a frequency above 0. We can never include the frequency 0 on the plots. Why? That's for two reasons. Firstly, we plot frequency on a log scale. Secondly, with the frequency 0, sometimes you find problems in calculating the frequency response. So we have to always start at a low frequency, at a frequency above 0. That's why I always write like that, the frequency which approaches 0, okay? Now let's take this example where all the factors are polynomials of degree 1. We start with the numerator. We have here a negative gain, so the corresponding phase is equal to 180, not 0. If you remember, for the first example we had a positive gain, that's why the phase was equal to 0. But here we have a negative gain, so the corresponding phase is equal to 180, okay? Now we take this polynomial, we can observe that the real part is not strictly negative, so the phase is equal to the inverse tangent of the imaginary part over the real part. We can observe for the frequency from 0 to infinity, the corresponding phase is equal to 90. Now for this polynomial, we also have a real part which is not strictly negative. So the phase is equal to the inverse tangent of the imaginary part over the real part. We can observe here that for the frequency from 0 to 1, the corresponding phase is equal to negative 90. But for the frequency from 1 to infinity, the corresponding phase is equal to 90. Okay? Now we start with the denominator. We take this polynomial. We can observe that the real part is not strictly negative, so the phase is equal to the inverse tangent of the imaginary part over the real part. We can observe that for the frequency from 0 to infinity, the corresponding phase is equal to 90. Now we have these two polynomials that we already plotted in the first example. Now we add all the curves corresponding to the numerator. Then we find the corresponding phase of the numerator. Then we add all the curves corresponding to the denominator and we find the corresponding phase of the denominator. So the corresponding phase of the transfer function is equal to the curve of the numerator minus the curve of the denominator. Okay, you can observe that we obtain the same curve that the function Bode in Matlab gives, where the phase varies from negative 90 to 90. Okay, just a little note, for discrete time transfer functions, we follow the same method, the same strategy I explained for the continuous time transfer functions. Just the difference is, in the discrete time case, we replace the variable z with exponential of GWTS, where TS is the symbol time. Okay, I hope the subject is interesting for you. Wait me for other subjects. And don't forget to subscribe to my channel. Thank you for your watching. Goodbye.